round 3. It looks like more graphs, and you're right, but we have a demo going along with this one too. First question here is, given this graph below, it's a position time graph, how would you describe the motion of the object? I hope we're all on the same page here, where position, time, you're increasing your distance at a steady rate, so this thing is moving in the positive direction, constant, right? Okay, I have my motion sensor over here, right there. Maybe you can see it, I hope you can. If you can't, it's over there by the window. And I'm gonna walk, so you gotta predict. I have to walk positive, I have to walk in the positive direction at a constant velocity in order to make this graph, all right? Make your guess, right? It's a prediction. There's no right or wrong answer, just take a guess, right? And we will pull up the Logger Pro. Clear. Okay. Are you guys ready? I hope you're ready. There we go. All right. All right, I'm gonna press the space bar. We're gonna go. All right, there we go. Now, let's look at that graph. This graph right here looks a lot like that graph right there, doesn't it? All right, and you know it's not quite shifted, right? But started, if time 2 is time t equals 0, then yeah, I start at some location. Whoop, this to me looks positive and constant, huh? Sure does. So, but is that how I walked? I didn't walk like that at all, right? Right? I was taking I took a step and stopped. Right? And then I was not walking at a constant velocity, guys, right? Took a step, stop, took a step, stop, took a step, stop, right? So what's going on here? What's going on here? What could I do? What can I do to make sure that the data is going to capture everything? Because it looks like I've got a false data, just like Dr. Wright. That's not how you walked. That's not a good description of how you walked, right? Well, what could we do? Well, let's go up to, stop that, there we go, experiment. Let's go to data collection. Let's see what data collection says. When I go to data collection, it says I'm going to collect data for 8 seconds, and it says I'm getting a half sample every second, which means every 2 seconds it's going to say, where are you, right? Now let's change that to say like 20, right? So it's going to take 20 samples a second, right? Now, what's going to happen? What's this going to look like? Is this going to look the same as what it was? Let's take a look. Come on now. Aha! Aha! All right. Well, this is interesting. So now that I've made the time between my samples much smaller, I can see, hey, this is where I took a step. 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 Right? And then I stopped right there. Stopped. And it's that pattern over and over. I can see that pattern now. Whereas before, what was going on? Right? Before, it said every 2 seconds, right? It put a dot right there, dot right there, dot right there. So it's like every few seconds, it would say, where are you? And then it would just connect those with a straight line. What's it doing? It's assuming between those 2 spots, I was moving at constant velocity. That's why it's connecting those spots with a straight line. This is interesting. At least I find it incredibly interesting. I hope you do too. So if I go F3, let's go back. Here we are. So what did I do? What did I do to do that? To see what was happening in between. Reduced time between samples, right? So the moral of the story here is when delta t, right, the time between samples is really big, right? What we do is we let's see if this will let me write. We assume, that's a little too big, right? Oh well. We assume that velocity is constant between the data points. Right? That's what we're doing. Right? Every single time we take two data points, the assumption is I am moving at a constant velocity in between. Right? Now, obviously not a great assumption when delta t is big, but how about as delta t decreases? As delta t decreases, what happens to the assumption? As delta t decreases, the assumption that I'm moving at a constant velocity, all right, assuming that there's a constant velocity, it decreases, right? The amount of assumption decreases. The time gets so close to each other that it actually seems that between these 2 points, I'm moving at a constant velocity. Now, when you add all a bunch of different little points together, eventually you can be speeding up. But what we're saying here is instead of saying, oh, we're going at about this velocity. No, what you would say is you would go back to this piece right here, and you'd say, Dr. Ray, at this location right here, between these 2 time points, let's do the linear fit here, right? At that point, you're moving at about 0.28 meters per second. But then between these 2 time points, right, you're moving like nowhere, right? 0.02. Whereas if I were to look at the whole time point between these 2 right there, look at this. This says, oh, on average, right, Professor Ray, right, I don't know what happened in between, but I know you were here at this time and there at that time. If I assumed you walked at a constant velocity, you're walking about 0.1225 meters per second. All right, so that's what's going on here. That's what's going on here. Let's see. Let me go back to here because we have a little bit more to do. Right, so the fundamental equation of velocity is exactly the same, right? Whether I'm talking about a big T or a little t, right? A big displacement or a small displacement. If I calculate a velocity, it is delta x over delta t, displacement over time. Only we give this kind of slightly different names. If delta t is big, right, I'm making an assumption that between these 2 time points, I'm moving at a constant velocity. And as that time point gets smaller and smaller and smaller, right, the amount of assumption or of what your velocity doing or what's happening between that motion decreases to where the average velocity eventually becomes what we call instantaneous velocity, the velocity at a particular point in space at a given time. All right, let's get some more practice with this. All right. So let's observe what it looks like on a graph when we're trying to, calculate this velocity delta x over delta t, right? But we have to first recall the slope of the position time graph, right? Slope of position time graph represents physically velocity. Right, that is what the slope is. Remember that, guys, right? You're going to get tested on it. You are going to get tested on it in class, on exams, on quizzes, in the lab. I mean, just really important thing to know, right? The slope of position time has a physical meaning. That is the velocity of the object, right? And so below we have here a pretty nice graph that shows the position time graph of the sprinter in round 1. Okay, so what we're going to do here is we're going to draw a line that connects dots 4 seconds and 24 seconds. So here's my 4 seconds, there I am, and then 24 is right there, right? So what could you do here, right? I could say, hey, what is your average velocity between these 2 points, right? I could say my delta v is equal to delta x over delta t. I could actually calculate, right? The time difference is 24 minus 4 seconds, 20 seconds, your delta x. Well, it looks like right here you are at about 25 meters, and down here you're somewhere about 50 meters. So you come up with that displacement to 75 meters in the positive direction. You could calculate what that v is. What have we essentially done? We have 2 points on a graph. We calculated how far did I go up, How far did I go over? That's your rise over your run. And when you connect these with a straight line, notice we essentially calculated our slope right there. We've calculated the slope. Does that, let's see, the slope. What does this slope represent, right? What does this slope represent? Well, it represents the average velocity of the sprinter between those two times. Is that how that sprinter was actually moving? No. The sprinter was speeding up a little bit until about 14 seconds, and then the sprinter was going at a constant velocity until about 24 seconds, right? Velocity was changing, then it was constant, but if I made this same trip from 4 seconds to 24 seconds, from about negative 50 meters to 25 meters, if I ran at a constant velocity of, I don't know, let's see what that is. That'd be like 75 divided by 24, of about 3 meters per second. I would have started in the same location of the sprinter, and we would have ended at the same location together. I would have been ahead the whole time, but then at that final little piece, the sprinter catches up with me, right? We would have tied the race, okay? So let's do this again, but we'll do this with a different color, right? We'll do this with blue, right? So I think you're supposed to label that first one A, right? Yes. This one is A, right? Probably should use the same color. But now I'm going to connect 4 and 10. Connect these 2 points. When I connect these 2 points, 4 and 10, right? Roughly right there. Select. I'm going to go right there. I'm going to label this B, right? What does this represent, right? The slope of this line represents the... You probably wanted to say instantaneous, but I wouldn't say this is instantaneous yet, right? This still represents the average velocity of the sprinter between those two times, right? Now, let's say we were trying to estimate, right, represent what is the actual velocity of the sprinter at time 7, right? So we want to know at time 7 right there, right, is line A or line B a better estimate of the actual velocity of the sprinter at time 7? I would hope you would say line, come on, yeah, line B, that's the one, right? But it's not instantaneous yet. When do we get to instantaneous? A good approximation would be if we drew a line that connects the dots at 6.9 seconds and 7.1 seconds. And what you'll see is this looks an awful lot like what we call a tangent line. Notice the graph is oh so similar in slope to B, but it's not quite the same. It is a better approximation than the previous one. And so as you start connecting these points that are closer and closer together, as long as you have the data, right? As long as you have that data, you connect those, you can calculate the slope right around that line, right? So if I want to know what's your velocity at 20, I would take at, the point at 20.1 seconds and 19.9 seconds, calculate the slope between those. That is a very, very good estimate of what the instantaneous velocity is at 20 seconds, or in this case for 7 seconds, we connect these lines, these dots at 6.9 and 7.1 seconds, and we get a slope. Now, those of you who are in trig, maybe calculus, you might remember this as a tangent line, a line that just kisses the curve and matches the slope at where it just touches that point of interest, right? So difference between average and instantaneous velocity, hopefully they're starting to click a little bit, because now we're going to ask some questions on it, right? And you see the caution sign, that means, oh my gosh, that means we have to do this. All right, don't worry, I'll help you out a little bit too. Below is a position graph of an object. what is the average velocity of the object between t equals 1.5 seconds and 3 seconds. So you have to locate, right, those points. You can actually calculate it, right? Delta x over delta t is equal to v to calculate your average velocity, or you can connect the two and you get a slope, right? So give this one a try. I'm going to connect the lines. So we have 1.5, here we are at about 1.5, and then at 3, I am right, let's see, am I at the right spot? I don't think I am. 1.5 is right there. Ha! All right, gotta be real careful about this, right? 1.5 and 3, connect those lines. I don't even have to do much of a calculation here. I see that's a flat line. I see a flat line. That tells me my slope is 0. But you could calculate this. V is equal to delta x over delta t. Delta x, let's see, x2 minus x1 all over t2 minus t1, right? Guys, if you're going to watch me do this, you're going to see me do this nitty gritty, right? Filling in all the blanks. 10 meters minus 10 meters all over. That'd be 3 seconds minus 1.5 seconds. That gets you 0 over whatever, which is 0 meters per second. Right? Velocity is 0. Now, does that mean you're moving at 0 the whole time? No, but it means that you started and ended at the same place. So I would assume, not knowing anything else in between those 2 points, that you were at rest. Right? Just like if you see me right now, if you close your eyes, don't open them. If you close your eyes, all right, now you open your eyes. I'm in the same spot, right? So my average velocity was 0. But you may have heard my feet running. I ran to the door and I ran back, right? My velocity wasn't 0 in between those 2 points, but my average velocity is 0. All right, I'm going to give you a little chance on this one. What is the instantaneous velocity of the object at 3.5? Give it a try. Okay, so 3.5, let's first locate that connection. If you got it right, move forward, right? So 3.5, here I am, right there. Now I want the instantaneous velocity at this point. Let's rephrase. So instead of saying instantaneous velocity, I am going to say calculate, or what is the slope, right? So when you are given a graph, position, time, and when you read velocity, you can insert, copy, paste, slope, right? What is the slope at 3.5 seconds? That's what you're trying to find. It looks like you're on a straight line at that point, so you can choose any 2 points on that line to choose, right? So calculate the slope of this line. I'm going to choose 2 points, right? You could choose any 2 points, but make it easy on yourself. I'm going to change the color. Right, I'm going to choose that point right there because that one looks pretty easy, and then I'm going to choose that point right there because that looks pretty easy. Velocity is equal to delta x over delta t. Not again, Dr. 8. Yep, here it comes again. x2 minus x1, t2 minus t1, right? x2, right? So this would be my position x2. It's later in. This is my position x1. Let's see. It looks like I'm at 0 here. And then over here at x1, I'm at 20 meters. So my velocity is going to be negative. Makes sense. It's a negative slope, which means I could come over here and do bam, 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 bam. Those are both gone. Now time at t2 is 4 seconds. 4 seconds minus x1, t1 is 2 seconds. I can see where this is going, and hopefully you can too. I can see clearly now. The math is done. Divided by 2, negative 10 meters per second. There you are. All right, do I have anything else going on in this round? That's clear. Clear. Oh, we do. We have more going on. Another one for you to do, right? When do objects, one would be this curvy guy right here, and 2, at the straight line right there, have the same velocity, right? There's your time t0. It's either going to be sometime before, sometime after, at that time, or never. Which one is it? Okay. So how are these moving? That'd be the first thing to figure out. 2 is pretty easy. It's moving positive and constant. 1 is moving positive, but it looks like it's starting fast and ending a little bit slower. So this here is positive slowing down, right? And who starts faster? 1 does. 1 starts faster. All right. Well, what is it? I want to compare velocities. Copy, paste. I want to compare slopes, right? If I want to know when they have the same velocity, that means I want to know when they have the same slope. So let's redraw 2, right? So there's 2, roughly about the same right there, right? So my question is when does 1 have this slope, right? 1 does not have this slope at the end. 1 does not have this slope at the beginning, but it has it somewhere in between. Where? Where is it? Right? Where is it? Where would you say? Nope, not the same slope. So I'm just trying to get this part right here where it matches. Yep, right. Probably somewhere right about there. You see how that line that I just drew looks like that one up above, right? I went between 6.9 and 7.1. I created that line that just kisses 1 point where it matches the slope, and that's this point right there. And that time, to me, looks like it comes before, right? So that means at this time right there, that's when 1 and 2 have the same velocity, right? 1 started faster. It's covering more ground at the start, but he starts to peter out, starts to slow down pretty rapidly after this time, where eventually at this location, they have the same location at time t equals 0, but 2 is now moving faster than 1. And so if the race continues, 2 ends up winning the race, slow and steady, right? So at some instant before t0. All right. I think this is the last one. A car is moving along a straight stretch of road. The following graph shows the car's position as a function of time. At what point or points do the following conditions apply? So we have position A, B, C, D, and E, and the options are where can they go? They can go displacement is 0, the speed is 0, the speed is increasing. I think those are your options. Are there any more? Nope. Next round comes after this one, guys. Okay. So, what I want you to do is give it a try. When you're ready to go, press the S. And we're back. Displacement is 0. That means wherever you are at this location is exactly where you started at the very beginning, right? So this is compared to the beginning. At the beginning I started at 0, right? When I get back to D, I'm back at 0. Nowhere else is my displacement equal to 0, right? Your speed is 0. Okay. Copy, paste. When your slope is 0. That means we have to look at these tangent lines, right? So at A, is your speed 0? Nope, it's not 0. How about at B, right? B, is your speed 0? Ooh, that looks like a pretty flat line to me. So B looks like it's 0, right? Try to draw those tangent lines of C and D, right? C is not perfect, right? But it's not 0. D, right here. Okay, and then E is purple. Oh, yeah, that guy, yeah, totally 0, right? So your speed is 0. Now, the difference between these guys here, so select speed is 0 at, text. Right? Speed is 0 at B and E, right? You might have been able to get E just like, oh, you know what, you're at rest. So that is definitely speed equals 0. B, maybe that caught you off guard. That's your turnaround point, right? Initially, you're going positive and you're slowing down. It's curving down, positive, slowing down. But then you stop and you start going negative, right? As soon as you go from a positive slope, if you end up with a negative slope, you have to hit 0, okay? B is that turnaround point. So your speed is 0 at that point. All right. Speed is increasing. Now you got to be careful of what we mean by increasing. By increasing, it means before you're moving slower, after you're moving faster, right? So I'm going to clear these, right? Because I can. So if I look at A, right? Before I'm moving with a bigger slope, after I'm moving with a slower slope, right? I'm slowing down. At A, I'm definitely not increasing speed, right? B, let's see, B, am I increasing speed? B is also kind of silly, right? It's like you're slowing down, then you're speeding up, right? B is that point, it's your point of inflection, right? I'm not really increasing my speed because before I was slowing down and after I'm speeding up. It's kind of a funny point, right? That's why it's a point of inflection. It's a point where you are at zero, you're changing direction, right? How about point C? Point C, it looks like before, to me, I would say C is certainly increasing speed, right? C is definitely increasing speed. You're moving negative slow, you're moving negative faster afterwards. So C, definitely. D is another one of those funny guys, right? It's a point of inflection where it looks like you're increasing, then you're decreasing. So this here, before we went from decreasing to increasing, it's where you kind of changed directions, right? You went from a positive slope to a negative slope, and then you're at zero at that point. Here, you have a negative slope and a negative slope. So here it looks like you're speeding up and then slowing down afterwards. So what does that mean? It means you've hit a maximum velocity here at D. So I wouldn't even put D there. And then E went over at rest. So for this guy, only one I would say that's increasing, not that my opinion is the only one that matters, but it might matter right now, is C. All right, guys, we did a lot. We did a lot here. Tangent lines, slopes, graphs, increasing, decreasing. There's so much information you can get from the graphs, guys. And hopefully, the more we work with the graphs, the easier this will come, the faster it will come. But you have to put in the work. You got to put in good practice. All right. Onward.